Okay, everybody, so now we've got a nice visual representation of the speed of the vehicle and how many feet it takes before your brain realizes you have to stop. So the number of feet from the time your foot leaves the gas pedal and covers the brake pedal. And what's cool about this relationship, this correlation, if you will, is its linearity. The linearity makes sense. This is all based on a 1.5 second perception time. But what's neat about the linearity is you can actually make predictions about how many feet are going to be needed to perceive the need to stop based on your speed. So for example, if you increase your speed from 20 to 40 miles per hour, you're going to increase your perception distance, this from 44 to 88. So as you double 20 to 40, you also double 44 to 88. You can triple. If you triple 20 to 60, you're going to triple 44 up to about 130 or so. If you quadruple, same thing. If you quadruple your speed, you're going to quadruple your perception distance. It also divides down. You could increase by 50%. So if you go from 20 to 30, you're going to increase by 50% here from 44 to 66. As a matter of fact, you can scale it all the way down. And since it's for every 10 miles an hour increase, it's 22 feet increase. That means for every additional for every additional mile per hour you increase, you add 2.2 feet of perception distance. And this is one of the benefits of the idea of a linear relationship, is that it scales. By definition, it's going to scale. So that's the slope of the line, so to speak, if you want to look at it. It's 2.2 over 1, or 22 over 10, or 66 over, I mean, there's any number of relationships you could write this out as. But the idea is it all reduces to 2.2 over 1. Okay, beautiful. Now, there are other, I'm going to, you know what I'm going to do real quick before I go any further. I'm going to left click on the trend line that I added earlier. And then I'm going to press the delete button just to get rid of it, because we're going to focus on the other data sets now. We're going to learn some cool stuff. So what we're going to do is I'm going to scooch the graph, smush it down this way a little bit. And you might notice something. When you click on a graph in Excel, like we just did here, you might notice it really helpfully shows you what data is in the graph. But what's cool about that is it's got these drag handles, just like we learned about a couple of days ago in the videos when we were dragging things down. And you can drag, I'm going to left click this bottom right corner and hold it and then pull it to the right. And when you do that, it actually adds those data sets to the graph. Now I'm going to scooch it over just a little bit for starters. You'll notice there's now 3 different data sets. We're going to have to change our graph because no longer are we just looking at perception distance. We are now looking at perception distance. We're also looking at the stopping distance on dry pavement, and we're also looking at the stopping distance on icy pavement. Now, the first thing, I'm going to pull this over again. The first thing I really think we should add is something called a legend. Because now with 3 data sets, unless you have the data that you're looking at over here, you're not sure which one is which over here. So what I'm going to do is I'm going to click back on my dispensary cross and add the legend right here. And when I check that, it drops in this beautiful, helpful little box that actually shows me the 3 different distances that are now being shown in the graph. So it's not just perception reaction distance, which is the blue. It's also the stopping distance on dry pavement, which is the red, and the stopping distance on icy pavement, which is the green. Okay, now let's also, I think we need to change some of these labels too. Speed in miles per hour is fine. There's no problem with that whatsoever. Perception distance, definitely we should just call that distance, because that's what we're actually looking at. And if you want the title, we can actually just go perception reaction distance and stopping distances on dry and icy pavement as a function of speed. I'm going to put that as put that in parentheses. I'm feeling a little bit saucy. Maybe make the font size a little bit smaller. There we go. That's not terrible. I mean, maybe make this smaller. I mean, now it's just a matter of at this point, it's just a matter of fine-tuning. You can put the legend on top of the graph if you want to and make the graph scooch over. There's all kinds of things you can do. So I'm going to put the legend back where it was. Okay, now we know that the perception reaction distance was linearly correlated. That means that the as our speed increases, the perception reaction distance increases linearly. Let's take a look at the stopping distance on dry pavement. Okay, now I'm going to do something to kind of help us clear this up. I'm going to temporarily take out the other two data sets. I'm going to left click on the perception reaction distance and press the delete button, and that removes that data set. And I'm also going to do the same thing for the stopping distance on icy pavement. So now I see just the stopping distance on dry. This is like we did with the perception distance, except we're looking at the stopping distance instead. And I'm going to add a trend line, just like I did with the perception reaction distance. And what's nice about the legend is it actually says linear stopping distance on dry pavement. Now, if you look at that line, you might notice a couple things. First of all, it doesn't really hit any of the points. And I want to say something about that right now that I'll come back to in the next series of videos. It doesn't have to actually hit the points at all. We're going to look at things called trend lines, are also called best fit lines. They're not called perfect fit lines. They're called best fit lines. So when you look at this linear trend line that Excel has put in, it does have one thing going for it. The faster we go, the more distance it takes us to stop when we're on dry pavement. The problem that I see is the line doesn't make sense as you look at it diagonally left to right. For example, if you were to continue this down to 10 miles an hour, if you were to continue this line down to 10 miles an hour, it would actually go negative. That doesn't make any sense. It shouldn't take negative feet to stop. As a matter of fact, negative feet to stop makes no sense at all. The smallest number of feet to stop should be 0, not negative. So that doesn't make any sense there. And then if you follow it left to right going this way, you might notice something. It looks almost like the points bend down and then bend back up. So like this point's pretty close to the line here. And these points are pretty close to the line here. But this one right here is really far away. And this one over here is far away in the other respect. And rather than draw you through all the physics that's involved with this, I'm not. We're going to left click on that trend line and hit delete. And I'm going to give you some I'm going to give you a quick little side physics lesson. I'm going to go up the trend line, but instead of just checking it, click this little arrow to the right and then go to more options. When you do this, it gives you a choice of which trend lines you'd like to use. Okay? You can pick exponential, logarithmic, polynomial, power, or moving average. Now, most of these have no place in Math 105. These are very much Math 111 type ideas. But what I'm going to encourage you to do right now is click through these options and see if you can find one that fits fairly well. Go ahead and hit pause, click through, and see if you can fit one that kind of traces out the path of those points better than the line does. Go ahead. Okay, my friends. So hopefully you've gotten a chance to kind of goof around a little bit. I'm just going to go down through the list. Let's start with exponential. We're going to talk about exponential behavior soon. Next topic, actually. Let's take a click on that. Oops, take a click on that. Okay, and again, this one, I mean, it's got a curve to it now, which I think makes sense. But it's still, it's kind of almost reflected what the line was doing. The line, this point and this point are on top, and these points are on the bottom. The exponential kind of went the other way. So let's keep clicking through. We know linear doesn't look too well. Logarithmic, nah, that's going the wrong way. It's bending the wrong way. It's bending that way versus that way. Let's try polynomial. Ooh, polynomial order 2. That looks pretty good. That actually is doing a really good job. Let's put that one on the back burner for now and keep going. Power. I think polynomial looks better. Yeah, I think so. Polynomial looks better. And moving average, yeah, not moving average is not good. Now, real quick, polynomial order 2, and this is the quick physics lesson, is the quote-unquote correct one. Not that you need to know this for Math 105, but the stopping distance, which is composed of the braking distance. We know that perception distance is linear, but braking distance is actually quadratic, which means as you increase speed, it's not as simple as with perception distance. When you said like, okay, if you double the speed, then you double the perception distance. That's true. But if you double the speed, you more than double the braking distance. If you double the speed, you actually quadruple the braking distance. Now, please make sure you're careful on what I'm saying here. I'm saying braking, not stopping. Braking is actually the distance it takes the car to, by the time your foot starts pressing the pedal down to the time it safely stops. So if you double the speed, you actually quadruple the braking distance. If you triple the speed, you multiply the braking distance by a factor of 9. And you don't have to memorize this statement. It's not important to memorize it. What's important is being able to look at the relationship in the graph and realize that that relationship is not linear. As a matter of fact, if I go back and delete this, I'm going to do a whole bunch of undos here and get my original data back. I'm hitting a lot of Control Z's right now and putting my original data back on, which consisted of perception distance. There they are right there. And if we look at just the icy pavement right here, the icy pavement, we can do the exact same thing with the trend line. And you'll notice that if you go to more options and you throw the linear model on there, once again, it's not correct. Polynomial order 2 looks fantastic. Looks fantastic. So the idea being not so much to know why braking distance is quadratic. You could actually check to see that braking distance is quadratic if you look back at the original data. Check this out. If you zoom in right here, look at the braking distance now. 20 miles an hour, braking distance is 20 feet. 40 miles an hour, that's twice as fast. The braking distance is 82 feet. That's 4 times as much. Does that make sense? 20 miles an hour, braking distance is 20 feet. 60 miles an hour, braking distance is 184 feet. 20 to 184 is 9 times. 20 to 60 is 3 times. So the important thing to look at is all 3 of these data sets go up as you go left to right. The important thing is to notice the correlations are different in each. With perception distance, when we try to put the trend line on, notice if you try to add a trend line with 3 data sets, it asks you which one you want to put it on. You can put a linear trend line on perception distance and it makes perfect sense because we analyzed that and it made sense to us. But when you try to put a trend line on the stopping distance, linear does not make sense because although it is rising left to right, it is not rising consistently left to right. It's accelerating as it rises left to right. And this is part of the danger of trying to stop a vehicle when it is increasing in speed. The perception distance is linear, but the actual distance it takes to stop the car is not. So congratulations, my friend. You just did your first little bit of data mining. I think we're ready to take a deeper dive into some more messy data sets tomorrow.